Welcome to the Talent Q webinar series. Thank you for attending and thank you to our speakers of today for accepting our invitation to talk about some hot topic that is the energy of the quantum computers. It's very difficult to present or to use Olivier because he's a well-known person in Europe, and in fact he's one person that is a reference, at least in the documentation of the status of the quantum computing around the world. Olivier Ezratty is in fact a French consultant, but he's also a professor, he's a researcher, he's almost everything, he's an analyst. And it has a very well-known, a very good book that is Understanding Quantum Technologies. If you don't know this book, try it because it's free. And he is doing a very good work writing this book and making available all the information about quantum computing. But for today, what is more important, he is one of the founders and one of the people that are involved in the Quantum Energy Initiative, that is a worldwide initiative to study the energy issues regarding to the quantum computing. The idea of asking, are really these quantum computers energy variable respecting the classical computers, or even can we have enough energy to run a very large number of qubits in the future? This is an important question. The second one is Yasser Omar, that is also a very well-known person in Europe. He was organizing last year the Quantum Year, and he was one of the responsible of this initiative, but is now and later is professor of physics in the Instituto Superior Técnico in Lisbon, and is leading researchers in the quantum information science, and he founded the QUTEP lab, Quantum Technologies Laboratory, and the Physics and of Information and Quantum Technologies Group, and is also president of the Portuguese Quantum Institute, that is also a well-known entity in the quantum technologies. Finally, but not the last or the less important, he is founder of the new startup Quantum Green Computing and is board member of the Quantum Energy Initiative. They will talk us about this quantum energy, last quantum energy results that they have because they have been studying these energetic issues in quantum computing. Again, thank you very much for accepting our invitation. For the people that are attending, you have the chat if you want to ask something later, because the presentation will last more or less 40 minutes. We have time for questions, and in this case we'll open you the microphone in order to make the questions directly to them. So Olivier, please start with your presentation.
Okay, thank you, Andres, for the presentations. And if I remember well, you invited us because you saw my presentation at Q2B, at least the slides I did share, because the videos are live now. So it's going to be a kind of replay and some updates on that. So I will start with presenting the QAI as an organization, and then about the latest thinking we have about the challenges of FTQC energetics. So just to explain you where the QAI is coming from. It comes from the thoughts from physicists, and particularly one of the co-founders of the initiative named Alexia Opheb. So she's a CNRS researcher currently based in Singapore. Back then she was in Grenoble when she published this paper, which was the kind of bootstrapping paper for launching the QAI. So basically, the idea behind this initiative is to look at the energetics of all quantum technologies, and not just computing, by the way. We look also at sensing and communications, particularly communication, because if communications and quantum communication scale, it's going to be probably driving some new energy consumption. And so we want to have, to kind of push the industry and academics to work on the energetics of those issues, of those technologies, and not just when it's ready to be deployed at scale, but before that, because usually you make choices in the design of the systems very early on, which may impact the energy footprint, and not just energy, also materials, product life cycle, recycling, and stuff like that. So we want to work on that as early as possible. What do we do and how are we organized? It's mostly about building a new kind of science and engineering discipline, very interdisciplinary. You'll see that in my presentation and with Yasser's presentation. We want to create also some methodologies and standards to help people evaluate, optimize, and benchmark quantum technology energy consumption, and not just computing again. Where do we show up? We're online. We've got our own website, of course. We organize a workshop every year. And by the way, the next one is in Barcelona, in Spain. So it's going to be in May. The last one were in Grenoble, in France, and in Singapore 2.5 years ago. We do presentations, particularly Alexia, Yasser, and me, and others, in various settings, like the APS meeting in the US. We were at ICQE in Italy, in Padova, last year. There was the France-Singapore Symposium last year as well. The Q2B, where I did a talk in Paris and in Santa Clara. And we organize also, from time to time, some online seminars. So that's what we do and where we are. Who are we? So we are a board, a scientific board, with 4 co-founders. So Alexia, we have Robert Whitney as well, who's based in Grenoble, and Janine Spletstosser, who's based in Chalmers, even though she's not anymore in the board. And we have a couple industry partners who are supporting the initiative. They don't pay us. It's just they support the initiative, and sometime, particularly at the workshop we organize every year, we have them doing presentations, invited talks, or contributing talks. And the community is about, 600 to 700 people now from many, many different countries. So now, what do we produce? What do we want to convey as ideas? Initially, 3 years ago, there was a paper written by Alexia, Robert, and the PhD named Marco Felusaziani about providing some ideas about how do you analyze in a full stack manner the energy consumption of a superconducting FTQC system. So it was the first ploy creating this kind of methodology. It's called MNR, and also listing all the energy consumption sources and making sure that we can estimate what would be the energy consumption of the systems in the future based on some assumptions. The second thing, and there's a connection with Marco, because Marco is leading the group at the IEEE, the P3329. It's a QAI working group that is working on the standardization of the way to assess the energetic cost of quantum computing at this point. Maybe later we're going to do something else. There's another project led out of France, which is about benchmarking and embedding energetic consumption in benchmarking. This project is also contributing to some European initiatives in that space. There's also a project which is run with Alexia and Robert and myself and EDF, which is an utility company in France, and Candela and Alice and Bob, to start with the problems of the end user, then look at the roadmap of those 2 companies, and then look at the fundamental science that's behind that, and making sure we have a kind of full stack approach to optimize the energetic consumption of a future FTQC system. There's a paper in prep where we have Marco, the IEEE guy. We have 2 guys from Candela and Alice and Bob, and we have Marco Pezzuto and Yasser Omar. And Yasser is there, so I'm very happy that he is there as well. And this is a paper in prep. We started working on that last year, and we hope to publish an archive, I hope, before the middle of this year. Then we also work together with Quick, the organization, and also with Yasser, to promote the embedding of the energetic topic in the agenda of the EU strategy, the EU quantum strategy. So that's ongoing. It's an ongoing effort, and we are very active on this thing. And the last thing I want to mention that's part of the QEI work is preparing a roadmap. What do we mean by the roadmap? It's assembling ideas, research questions from multiple organizations. I mean, it can be academics, it can be industry vendors, as transversal as possible, to make sure we have a kind of global idea about what we should do to look at the energetics in a interdisciplinary way. So we look at interconnect, software, compilers, error correction, quantum thermodynamics, quantum energetics, everything. I mean, we want to assemble the ideas from all the fields to look at this thing. So the rest of my presentation is going to be focused on this paper we are working on. Just to give you an idea about the breadth of the thinking behind the QEI, we have to look at the size of the problem we want to address. And today we don't know yet what's going to be the size. We don't know yet how many quantum computers will be sold in the future. We don't know what's going to be their power, at least for now. And one way to assess the size of the problem is to look at comparables. That's going to be the bulk of my presentation. So this is a chart that you may know, it's in my book. It's splitting energy consumption and power consumption in the world. It's a bit old, it's 2-3 years old because there's no more recent data. And it shows the consumption, particularly in that data centers and the server side. Everything that's in purple and green comes from end user devices, so we don't care about it. So we look at the data centers. And what we have here is interesting data. If you look at the HPC world, so supercomputers, which are used mostly for scientific computing, it costs only 0.5% of the total ICT energy in the world, at least 3 years ago. And then if you look at the cloud that's being used by companies to do their ongoing business, it's much larger. It's about 20% of the total. So one question we have, I don't have the answer, is will quantum computing be an extension of the scientific computing activity that we have with the current HPC in the world, or will it be an extension of the cloud services that are used by companies? And this is very dependent on algorithms. It's very dependent on finding the good algorithms which bring an exponential speed up, a practical speed up. We know that for quantum chemistry and material simulation, it may work, but we are not sure about it for business applications like machine learning applications, like optimization application. There's more uncertainty. So it gives an idea of how to size the problem. Then another way to size the problem is what's the energy consumption and the power consumption of existing HPCs. And so if you look at this chart, on the left you have the applications. It comes from the DOE in the US. And on the right you have the distribution of the power consumption of the largest HPCs in the world. So the numbers you got to remember is we have only fewer than 10 HPCs which consume more than 10 megawatt, and you will see why I do that. And there's about 100 HPCs which consume more than 1 megawatt. So it gives an idea about the cost that people are okay to afford when they do scientific computing in the world. And another interesting thing is half of the investment in scientific computing is public. It comes from academics, it comes from big research organizations like the DOE in the US. We have all the Euro HPC program in Europe. It's mostly academic. But 40% is coming from industries who want to have their own HPC. So now, how do you look at the energy consumption of the system? Now let's look at a more kind of bottom-up approach. The beginning of my talk was a top-bottom. Here, bottom-up. The energy consumption comes from 3 main things. It comes from control photonics and electronics, which control the qubits. Then we have a lot of classical computing that's making the computer work. And 3 key functions. One is the classical part of quantum algorithms, because any circuit has to be generated by some classical software, and it may be very costly. Then we have code compiling and optimization. And then we have mostly the machinery behind QEC, so error correction, which may be costly. We don't know yet what's going to be the cost. And then there's, of course, cryogenics and vacuum. It drives some fear with a lot of people, although I'm not sure it should be the main fear. The main fear, if you are very forward-looking, is the yellow part. It's mostly electronics and lasers. This is going to consume more as we optimize the cryogenics, if you look at the plans from companies like IBM. So it's going to be important to look at the middle here. And all this is influenced, of course, by the quantum part. So the qubits themselves at the lower level, they drive noise, and the noise drives the need for error correction. And so you have the encoding rate for the error correction, which drives the overhead of all the part on the right. And so we fight noise with our correction. That if we can optimize that on the quantum part, it's better for the part on the right. And sometimes we have interesting ways to do that. We have engineering dissipation, even error correction is driving entropy. So we have to evacuate the entropy in a thermal bath. So there's a lot of, what's interesting is that simplistic chart is there's a lot of connection between the quantum part, how do you optimize the quantum part in quantum physics and quantum energetics and quantum thermodynamics, and the rest, which is classical and which is dependent on the connection. And of course, the software plays a key role, probably an underestimated role in the cost of those systems. So in the paper we're working on with Yasser and the team, we're trying to provide a kind of very global way of looking at the problem, and with a mix of science and engineering. So we want to decompose properly the consumption like we did before. We want to estimate the baseline cost of the system without optimization. Then we want to look at the various ways to optimize the energy consumption and look also at what's going to be the advantage of optimizing. And then look at operational aspects of that, because there's going to be a lot of operational aspects. And in the end, measuring, benchmarking, and standardizing. And also, that was the beginning of my talk, look at an economical view, not just a scientific and engineering view. So it's kind of very interdisciplinary way to approach that thing. So then I give you a couple ideas that come out of our work. The first one is how do you optimize? So the first thing to do is to do a good inventory of the energy consumption. So look at the baseline consumption. So based on some predictions, because if you look at an FTQC system with, I don't know, hundreds of thousands of electrical qubits, you can be based on extrapolating current consumption on these systems, or you can embed some kind of advances that are in the roadmaps of the vendors. Then you can apply a method, we call it a reductionist optimization technique, which is to look at individual components like cryogenics, for example, where you can improve the efficiency of those systems, but without affecting the rest. So let's say you improve the energetical lead of some cryogenics and you don't touch the qubits and doesn't change anything on QEC or whatever, it's going to be an independent optimization. And so we have to assess what's going to be the energetic gain, power gain with doing this. Just 10% in that example, it's just a theoretical example. And the last one that's the most important is what can you do with a so-called holistic optimization, where you look at things and you know that there's going to be some interdependencies between the figures of weight. So typically, if you change the electronics, you put some cryogenic electronics in the cryostat or superconducting qubits, it's going to change the whole balance. I mean, the cabling, you're going to have maybe some impact on the quality of the control signals driving the qubit and so on. So we know that there's going to be a lot of interdependencies. And then you can have some more optimization. The other thing that's part of our ideas is you have to make a difference between what you optimize in the system itself, and it's boiling down to the power it consumes, which is more or less stable, and the optimization you do at the energy level, which is based on the task, because a task consumes some energy, a system, independent of the task, consumes a power. So what and what how. So another question we ask ourselves is, if you look at this chart, it's 2 years old, we know that for many computing tasks, particularly quantum phase estimates and chemical simulations, and even Shor factoring, even though it's useless, it's going to be costly not only in the physical overhead, but the time overhead is going to be significant in some cases. So we know that the computing time is going to be a problem. So there's some ideas we try to work on, which is look at the way you balance the trade-off between the total energy of your circuit, where you can do some optimization at the circuit level and compiling level, the stuff you can do to accelerate the pace of computing, so faster gates, faster QEC cycles. And then the last one, which is potentially to parallelize your computing across multiple QPUs. And then you're going to be faster at the expense of having more power. You spend more power to save time. The watt hour may be the same, but but this has a lot of technical, I would say, impact, but also an economical one, because you can do that only if the QPUs are affordable. So we call it EFP, so efficient, faster, parallel. It's just a nickname. So now, if you look at what the power estimates are based on the roadmaps of companies, and there's this paper, I was interviewed by Karmala Pallavi-Kalagan when I was in the US last December, and she summarized the ideas. If you look at Continuum, which currently has an ISK systems that consume about 34 kilowatts, it's very modest. I mean, it's comparable to 1.5 rack of NVIDIA DGX, so it's not that big. Then if you look at Alice and Bob, a partner of the QEI, and we work with them, they plan to support 100 logical qubits and 1 million gates with about 160 kilowatt. It's very reasonable, but it's not a couple thousand logical qubit yet. Then if you look at IBM, in December, maybe the same day I was doing my talk in the US, Jay Gambetta, the chief research guy there and who leads the quantum team, advertised that there are 200 logical qubit system that should be there in 2029. It's going to consume 1 megawatt, and 4 years later, 2,000 logical qubits and trillions of gates will consume 4 megawatt. And then the worst case is PsiQuantum, which says that its own system for 100 logical qubits is going to consume 100 megawatts. It's a lot. So you see there's a big discrepancy between those vendors who published some data and some information. And so I summarized that in this chart. And this chart contains a comparison in power, not energy, in power, of the first estimates we have from vendors. And I put the threshold at 4,000 logical qubits and 10 power 12 gates. It's kind of the middle of the road for quantum chemistry and quantum chemical simulation, although some progress may reduce the need for key chemical simulation. And what it shows, that's very interesting. What it shows is based on the technology, based on the roadmaps of vendors, you have a 1 to 1,000 ratio of energy consumption in the plans. We don't know yet which one's going to work first. We don't know what yet is there's a correlation between those different technologies. So vendor A is PsiQuantum, the 100 megawatt, which I extrapolated to more. That's based on the information I got from them. In the middle, vendor C and D, it's a mix of Google and IBM. And then vendor E and others, it's a mix of Alice and Bob, photonic systems with more efficient photon source. It can be cold atoms, it can be trapped ion systems, which are planned to be cheap, although they are slower. There's going to be a trade-off between speed and price and energy. So when you make that comparison with the gray ones are the largest HPCs in the world, at least until I go to EDF, our partner. EDF is a small HPC. It's 1 megawatt, 1.2 megawatt. It's a typical HPC used in a large corp. And so on the right, you've got the numbers of HPCs consuming this energy. So below 1 megawatt, between 1 and 10, between 10 and 40. And so it gives you an idea of what's the existing market for a given power consumption. And so what my guess, it's a total guess right now, an economical guess, is given the prospective value from quantum computing, I would guess that the market size would be kind of similar. So if we have a lot of QPUs costing less than 1 megawatt, maybe we're going to sell hundreds. But if it costs more than 1 megawatt, maybe it's only going to be 100 megawatt, particularly for scientific computing. If it's more than 10 megawatt, maybe the market is going to be small, because it's going to be maybe 15 units. So the energetic cost, and of course the capex, so the cost of the system on top of energy, is going to be determining the size of the market, because most of that is academic. They don't have infinite budgets. They won't spend billions of dollars like for breaking RSA, like the NSA would like to do. So that's going to be an interesting thing. So I'm finished on that, and I will let, of course, Yasser do his presentation, because he's going to get deeper in the way we analyze the energy consumption. He did very interesting work on cold atoms and trapped ions and even other kinds of qubits. So he is extending the ideas that I was presenting. So just some advertising. We have this workshop in Barcelona, 18th to 22nd of May. So it's free. I hope we're going to have a lot of students and academics and industry vendors from Spain, because it's based there. And we already have some speakers, even though it's changing every day. So we have a couple of speakers there. For example, Michael Vasmer from INRIA, France, who is a guy who came from Xanadu, is a QEC guy. Natalia Ares, who's from Controlox and Oxford University. And Fernando Brendao, I think he confirmed. So we have some confirmation and some new speakers that are coming up. You can get the slides. So take your phone and take a picture of that. You can get the slides right now. And I leave the floor to Yasser.
Okay, thank you very much, Olivier. So first of all, let me thank Andres, Alberto, and Javier for the kind invitation to us and for all the organization. Thanks, Olivier, for the great talk. It helps a lot what I'm going to say next. And thanks everybody for participating. It's a great pleasure to be here. So let me get my presentation in full screen mode. I hope this works. Okay. I guess you can see it. So let me tell you a bit. Can I organize the windows? No, I can't. Okay, I'll leave it like this. I'll tell you a bit about some work we've been doing on the energetics of quantum gates and quantum processes. So first of all, let me still wish you a happy International Year of Quantum Science and Technology, because it's still on. The closing ceremony is exactly in 1 week. So we still have 1 week to celebrate, but more importantly, the International Year is just the beginning of something, longer and larger. And so the activities will continue, in particular with the World Quantum Day and the Quantum Cities Initiative. So your city can become a quantum city. Just, follow the World Quantum Day for the next steps. But so let me tell you about very briefly the origins of quantum computing. I guess most of you will be familiar with the ideas of quantum simulation from Richard Feynman in 1982, and then David Deutsch in 1985 with the idea of the universal Turing machine. But in fact, I would like to also mention Paul Benioff, sadly deceased, who had an independent way of suggesting a quantum computer. So in fact, he was very interested in non-dissipative classical computing. So at the time it was only called computing. And so he was interested in reversible computation, like many others in the 80s of the last century. And this was and remains a challenge for a bunch of reasons, to have a fully reversible classical computer. And the motivation is that if it's reversible, then it should not dissipate, at least at the fundamental level, at the logical level, let's say. And so he realized that, the quantum dynamics of a closed system is a reversible operation. And so he had this idea of using quantum dynamics to implement a reversible computation. So I would like to credit him also for an independent, proposal of a quantum computer. Coming back to the energetics of quantum computation, we have in my group and now in our startup, Quantum Green Computing, a comprehensive view that we need to address the energetics of the following components. So first, at the core, of course, is the quantum gates, the quantum circuits, the quantum information processing. Then also what we call the quantum data buses, so, moving the quantum information around. Classically, this is where most of the dissipation happens in the wires. Then, of course, something that is very important is all the classical control of the quantum hardware. This is essentially classical computation. And so the scaling of this classical computation that controls the quantum computer will be key, because we know how inefficient the classical computation can be. And finally, what we call the baseline costs, but here meaning, all the costs, energetic costs of running your experiment. So, your lasers, your vacuum system, your cryogenics, if you have it, etc. So this is how we see it. And so the question is, can we use quantum computers, quantum gates for better energetic performance? And this is, I think, a big question mark. And it's great, this initiative and context that Olivier gave. I think there's still a lot to do. This is a big, big question mark. I think the answer is not clear or obvious at all. So let me briefly, also convey that there's been very interesting work done at the more fundamental level, closer to, at the thermodynamics level, sometimes called quantum thermodynamics, understanding the energetics of single qubit gates and connections to the laws of thermodynamics. So given it's a short seminar, I'm going to go just for the essential points of each slide, and then I'll be happy to come back and discuss the details. There's also this methodology that Olivier already mentioned, developed by Marco Felozaziani and collaborators to try and give a framework that is proving useful to study this energetic performance in quantum systems. And so here I want to share with you a bunch of results that we've been obtaining over the last few years. Mainly, we are working here on the quantum gates and also taking into account typically what we call the baseline costs, so the costs of running the experiment. We are not yet addressing properly all the issues of classical control and corresponding scaling, and I will very briefly mention a preliminary result. I mean, it's published, but it's a first result in the direction of low dissipation quantum databases. So let me start with actually a pretty crazy idea, which is, could we use quantum dynamics as a resource for classical information processing? Meaning, could we use quantum gates for better classical computation from the energetic point of view with more efficiency? So this is something we developed. So this work was led by João Moutinho together with Mark, Sagar, Francisco, and Antonio in my group, a collaboration with Silvano De Franceschi from CRI in Grenoble and Sugato Bose from University College London, and we actually got a patent out of it, although we didn't expect it at the beginning. But let me tell you the key idea. So, a classical computer, you have the core is the CPU, the central processing unit, and the core of the CPU is something called the arithmetic and logical unit, and the core of the core is actually a circuit called the full adder. Essentially, it's a circuit that adds bits, and this is really the core of the classical computer. So we set to understand if we used quantum gates to implement a classical full adder, could we get some energetic advantage? So again, I will skip through the details, just convey the key ideas, and can come back later to the details. So first, let me give you our benchmarks. So the first two bullet points are the important ones. Essentially, if we look at the time, what was the fastest supercomputer, Frontier, and the most energy efficient supercomputer, Henry, essentially the energetic cost was around 10 to the 5 electron volts per bit operation. Then we found that there are some classical approaches that are still at research level that could have much better energy performance, but this is not really, to the best of our knowledge, really an actual solution. So this is ongoing research, and let's see exactly how it develops and if it requires some cryogenics, which then, of course, will make this performance work. So our numbers to beat is 10 to the 5 electron volts per bit operation. And so what we did, we devised a quantum approach to a classical Fredkin gate. This is a fully reversible universal gate. It's a control swap. Again, I skip the details, but essentially there's a circuit to implement the full adder based only on this Fredkin gate, which we could compress to just 3 qubits. And then we had the concrete proposal with charged qubits based on semiconductors and a way to operate this. But with essentially 3 quantum dots, we could do this. But let me jump to the results. And the results are actually quite bad. Okay, so I remind you here the state-of-the-art quantumly, classically, that we want to beat 10 to the 5 electron volts per bit operation. And what we got with our full adder looked much better, so 10 to the minus 2, much better, or 10 to the 5, competitive, but this is not taking into account the cooling. And for these semiconductor technologies, these quantum dot technologies, you would need significant cryogenics, and this was not at the time at the point where these ideas could be implemented experimentally, so we had to extrapolate a bit, just from a bit of thermodynamics, what would be the energetic cost, including the cryogenics, and then it becomes either competitive with the current classical systems or actually much worse. So this is not surprising because these systems are not at all optimized. These quantum gates are not at all optimized for energy efficiency. And so the first message is, this optimization is, as I think Olivier put it very, very nicely and clearly, this is there's a lot to do at this level. And people building quantum gates, quantum computers, until recently, they were mainly focused on performance for time, not for energy, although this is, of course, now changing. But also, I want to tell you that immediately by thinking about this energy performance, immediately some ideas started emerging how to improve this performance a bit. But the first message is not competitive and a lot to do in terms of improving, optimizing the efficiency. Then I just will mention this result is a very nice idea of how to transfer qubits from one place of the process to the other, just using spin chains and just using the natural spin-spin interaction. And so this is a very low control that system that doesn't require much energy. And so it's a very, very ideal case, but essentially we could, with this idea, and I want to credit there Sugato Bose and his student Dylan Lewis, and together with João and Antoni from my group for developing this. So it's a first idea of how if shuttling qubits around is costly, this could be a solution. Of course, here we are considering the solid state scenario, and in particular semiconductors, although this could, of course, be implemented with other systems like atomic systems that can emulate a spin chain and so on. But these results were entirely theoretical. We didn't really have any experimental measurements. And what we found as a system where we could do experimental measurements was with the group of Christoph Wunderlich, an experimental ion trapper who also has a quantum computing startup called Electron with a Q. And so this was a collaboration with Patrick and Christoph, and together with Sagar from my group and Sugato Bose from UCL. And so we wanted to implement this full adder with classical full adder with quantum gates and make some measurements. At the time, they only had a processor with 3 quantum bits, so we could only implement a classical half adder. So I skipped the circuit. We can come back to this. But the point is, for the first time, we were measuring, Christoph's group was measuring the cost of implementing these quantum operations. And so all the numbers are here, and 2 messages. The first message is that what really dominates is the cooling system, Doppler cooling, and especially the sidebed cooling. So, for example, the actual half adder, which is the Toffoli's and the C0, you see is here is much smaller. It's 1.5 millijoules in total, compared just the sidebed cooling, 35 millijoules. The second message is this approach that we did here is 12 orders of magnitude worse than what you would do in a classical computer. Okay, so not competitive at all. But again, none of this was thought to perform better energetically, and just without doing any work besides this, just by thinking a bit about how these things are implemented in trapped ions, immediately some ideas emerged that could potentially lead to an improvement of 5 orders of magnitude without much deep thinking. So this is another important message, and reinforce the message of how this optimization can produce some results, still to be open if this is competitive or not. Then I want to tell you about the energetics of, then we now shift to really processing quantum information. And this is a work done by Francisca and Marco, and that we actually never submitted for publication. It's about the energetics of trapped ion quantum computation based on the measurements we had before. And we rushed to put the paper online because of the master thesis of the student Francisca, and then she left and went abroad, and we never really finished polishing the paper, which we should finally do, because we now have a bunch of other results coming out and we want to include this. But this is, as you know, many of you will know this phenomenon that the students leave and the paper hangs. But so essentially the idea was, okay, now we have numbers from the previous paper in collaboration with Christoph Wunderlich. Let's do some quantum computation, some stable quantum information processing task. And so we chose the quantum Fourier transform and estimate, based on the previous numbers, what would be the energetic cost of implementing this very simple quantum computation. So again, we were based on an approach that was developed by Christoph Wunderlich and his team to implement a quantum Fourier transform. That's the reference down that you can see. He has this 3-qubit trapped ion quantum processor in a linear Paul trap. And so this would be the circuit to implement the quantum Fourier transform. And so these are the numbers we got. So based on the previous measurements of the, Doppler cooling, etc., all the things we measured before, with the circuit, we could now estimate the costs of implementing a quantum Fourier transform and all the other associated costs. And again, as you can see here, the actual information processing is not costly at all. And what is really dominating is the cooling here, 3 orders or 4 orders of magnitude or higher. And then what we could do, we could compare this performance of this ideal quantum Fourier transform, so no error correction here, and compare, extrapolate how this would scale with the number of qubits. Here in blue, this is the energy cost in joule for a certain number of qubits, n, and then we compare this to the 2 most performing classical computers, Frontier and Henry, and if they implement the discrete or fast Fourier transform, the classical Fourier transform, let's say, and we compare, and we see that there's a big difference. And so where does this difference come from? So first, these steps is because we are assuming the best the Christoph Wunderlich could do with their traps would be to have 7 qubits. So if you wanted, based on these numbers from the previous experiment, if you wanted to do more than 7 qubits, you would have to go in sets of 7. So there would be a cost that we did not take into account yet of, coupling these or somehow parallelizing these different traps to scale. This is not taken into account. The second point, we did not take into account any error correction. So in this ideal scenario, taken with a grain of salt, we can see that, the energetic performance is much better for the quantum operation than for the classical operation. But, of course, there's something hidden here, which is the computational speed up. Okay, and so this is something that still needs to be discriminated in the future and benchmarked. And so this was the first attempt, and it was the first time we could estimate the cost of a quantum computation, however ideal, based on actual measurements. And of course, we wanted to go, let me just quickly check the time. I should hurry. We wanted to go for error correction. So Enrico Trombetti led a very interesting work based on, assuming, based on Quantinuum's H2 trap dyne device with 56 physical qubits. Essentially, all these are results that are still not published, that he could estimate the times of all the components, including the error correction. So now we would need numbers from the experiments to transform these times into joules. And so this is in some sense unfinished work because of that. So I move on. But we do want to look at the error correction. But we also started looking at other platforms. So I go very fast. Oscar and Marco looked into Rydberg Atom quantum computer. This paper was put in the archive last month. And essentially, we kept the same. We want to compare different platforms. So we did the same quantum Fourier transform versus classical Fourier transform in this new platform, which is the Rydberg quantum computer. And again, we have the same behavior. Classically, you see these red and green dots go scale exponentially, whereas quantumly, it scales in principle as a cube. Again, this is an ideal scenario without error correction. Again, there is the computational speed up playing a key role here, still to be discriminated. But we started looking into the different components of the trap dynes, and so I go a bit fast, but we could see here discriminate what is the cooling, initialization, and measurement of the system here at the bottom. Then the actual cost of the computation is here in red. The cost of keeping the optical traps is this yellow thing, and then the total, and we cannot see it because it's covered by the window, but we have here on the right the different scalings, and of course the classical scaling is much worse. And we're looking at other platforms. Let me rush, but so this is unpublished work that we hope to put in the archive quite soon. So please don't take this with a grain of salt. And so we looked at superconducting cat qubits. This was Pedro and Marco from my group, and so here are some very interesting preliminary results. So first, here we are now considering error correction. This is in the wrong. Okay, I made a mistake. I put the wrong. Okay, this is the right slide. Sorry, I made it. There's a an ordering error here. So these are the results that Pedro obtained. And so again, we are comparing the classical fast Fourier transform here in black. And then this is the two supercomputers, now Jedi and El Capitan. This has been updated to the most recent supercomputers. And this is the quantum cost of implementing this. And so here's classical in black. There's two computers there versus quantum, and the same here. What's the difference between left and right? And then I'll go to the thing in the bottom. The difference in between left and right, this on the left is just the core, let's say, of the computation. On the right, we consider all the what we call the baseline, okay, and cooling and so on. And so we see that the scaling remains more or less the same, but we sort of shift to the right, so it's essentially a prefactor. It doesn't really affect the scale. The other message here, and again, these are preliminary results, is if we now optimize over the number of physical qubits per logical qubit and a certain and many other parameters, we can bring the blue curve to the green and yellow curves here. So this optimization can make a big difference. Okay, so these are the messages. Scaling doesn't change with the baseline in this case. We'll see now another case where it does, and then optimization can make a big difference. So now let me credit João Santos and Marco from my group, and Jay and Tristan from Quobly on the energetics of semiconductor qubits. And now this is the right plot that was in the wrong order. So again, this has on the left without error correction, on the right with error correction. Again, this is unpublished and preliminary. The key message, this is the same comparison of the classical, which is here in red with the quantum, but now it's in logarithmic scale. But so without error correction, the costs of cooling are dominating the energetic performance. But if we now put error correction, then the instrumentation, the currents, the manipulation of the gates, it's hidden here, but becomes dominant. And so it's actually not obvious what are these. So the things will change case by case. This can change also with the type of error correction we do. Then the decoding of the error correction can become dominant. So the message is there's still a lot to understand. Things will change for different systems. And essentially, I just want to credit some ongoing work on photonics with Gonçalo, and more recently we started looking also into NV centers with Vicente. But let me conclude. Essentially, my message is that there is still a lot to do. Things will depend on the system, on the approach, on the different optimizations you can run. This is becoming, companies are very interested, but they don't want to publish. So this is, they want to understand, but not publish the results. So this is moving from science and engineering, and there's a lot to do. I want to credit my group and funding that has been supporting this research, and that has allowed us now to create a company dedicated to investigating these topics. And so we are hiring for quantum green computing and also for the academic front at the Portuguese Quantum Institute. Thank you, and sorry if I took too long. Let me finish. Thank you.
Just in time. Thank you very much to both of you for these nice and inspiring presentations, because clearly the energetics of the quantum computers is really a hot topic for the future if we want to have real quantum computers in the future. We have a couple of questions. Maybe, Alberto, you can open the microphone to Karen-san that puts a question in the chat. If not, I read the question.
I can answer the first ones. I see.
Okay.
There was a question on comparing the HPCs and quantum systems. Of course, these are not the same workloads. I'm comparing the power consumption regardless of the workload. It's not normalized the same way. It's normalized against a number of logical qubits and number of gates that are supported, because we know that the overhead of error correction depends on the circuit size. So it's normalized for the quantum systems. So then let's say you want to run some quantum chemistry with 1 billion gates on 2,000 or 4,000 logical qubits. In this case, it's going to be an even comparison between the systems. And of course, HPCs, They can't do that right now. And so we're going to be in a regime of quantum advantage in that case. If you look at the HPCs, you can't compare them the same way because usually the more expensive they are, the more flops they support. And when you want to look at the energy efficiency, which is not showing up in the chart there, you look usually at flops per watt. And currently the record is with some of the largest systems in the world, 60 to 70 gigaflops per watt, if I'm not wrong. So that's the idea of the comparison. It's more an economical comparison. It's just to look at what's going to be a power drain, what's going to be the weight on the infrastructure. Because if you install a new QPU somewhere, you're going to have the infrastructure to support it. So the HPC sensors, they have some constraints, and you have to consider the constraints they have. And there was a second question which was more or less linked to that. Maybe the person who was that? It was Karen Singh. Maybe I can rephrase the question, or I can answer it right away, as you like, guys. Is Karen Singh still online?
Yes, I am.
Yeah, go ahead.
Yeah, actually, my question was actually first of all based upon the assumption of the normalization, but as you mentioned, the constraints and other things, and the overheads as well. But yeah, I think it's pretty much clear about the based on the answer you provided. But I actually have a follow-up question. Like, if I understand, because of these constraints, we obviously have we cannot credibly say that we have an fair comparison. But can we just use this particular graph or the particular variance to actually use for the analysis of the energy consumption of different types of quantum machines with respect to the particular input, like as they scale, just as a scaling trend? So that was actually intuition of the question.
Yeah, I got it more or less. I will try to respond that. Is your question related to the kinds of qubits, for example, trapped ions, cold atoms, superconducting qubits, or something else?
No, it was basically related to the particular energy consumption with respect to the input size. So if
the input size,
different types of
there's a difference between the power and the energy. The energy is what you're going to consume to solve a given problem. So if you have 1 million or 1 trillion gates, it will last some time, and you have to estimate the computing time, and then you multiply by the power of the system if the power is stable, which is still unknown depending on the qubit modality. So the power is different from the energy. The energy is linked to a task. The power is linked to a system. You put it on, and then you may guess that the power is stable or is not stable. So maybe a minimum, an average, and a maximum. What we know as of today is in most of the systems being designed, the power is going to be more or less stable because it's going to run a circuit, and we know that cryogenic will still run. We know that electronics will run, and there's a kind of on power that's always there. So the first guess we have is the power is going to be more or less stable. But then there's another maybe sub-question from your question is, how about the discrepancy between the qubit modalities, the kinds of qubits, a bit in line with what Yasser did present. What we know as of today is some modalities like cold atoms and trapped ions may be on the right part of the chart I did present, but they may have an overhead in computing time. So they may be slower. So if you want to have a good assessment, you have to look like the EFP framework. You have to look at the power, the computing time, and the energy. So these are three figures of merit which are important. Because as an end user, if I was an HPC end user, I would care about both the cost, so the energy is a cost. I would look at the power, which is a cost of the infrastructure, because you need to have the power lines to get into your center. And then I would look at computing time on a per task basis. What I have observed in trying to consolidate in a hectic way those data is that some qubit modalities are definitely on the right, but others may be both on the right and on the left, depending on the way it's being implemented. So, for example, if you have a biased noise qubit, it may be less expensive than classical transport qubit. Even in photonic system between Candela, Xanadu, and PsiQuantum, the energy efficiency of the photonic source, whether it's deterministic or not, has a huge toll on the energy and the power consumption. So it looks that it's a very open field, I would say.
Right. I got it. Thank you very much for the explanation.
Uh,
Any
any
question
uh,
for
we
Yasser?
have a second question from sorry for pronouncing wrongly, for Roger. That is Sampo who no and go.
So is this the question regarding reversible computation by Karen, right? So
Yes.
the question is the primary challenge faced in implementing reversible machines while consuming less energy. And so there was this idea since the 1980s to develop a classical reversible computer. But the problem is that by being reversible, this increases very significantly the circuit size and also the memory requirements, right? Because you need to keep track of everything. And so this never really worked in practice. So the idea is fascinating and beautiful from the scientific point of view. It would have the advantage that then you would no longer have dissipation coming from the most fundamental aspects, so Landauer's principle, and essentially connecting, logical reversibility or irreversibility to thermodynamic irreversibility, therefore changing the entropy and inducing a dissipation. But in practice, this never succeeded. The complexity is just too large. Quantum computation, the standard model of quantum computation, is actually reversible, so it has to take into account all that, but in a natural way, because it's it's Schrödinger's equation for a closed system. But it does have a cost that we don't really realize in terms of making the circuits larger, etc. However, this is not changing, and in fact, whenever there's a quantum speed up, this in fact doesn't make this doesn't compromise the speed up at all. And so the classical agenda of reversible computing didn't succeed, and for the reasons I mentioned, for practical reasons. Quantumly, the cost of reversibility is not compromising the performance in any way.
Okay.
Got it.
There is
Thank you.
one.
Thanks.
There is one question, and the last question because we are out of time. That is about distributed quantum computing. In fact, it's a question that I have because Olivier said that you can distribute the shots, but you know that there are another technologies that allows to distribute the circuit itself using quantum.
It's different things. It's two different things. What I was mentioning is not that, but I will comment on the question. What I was mentioning is run the same circuit on different systems. We do exactly the same stuff. Because when you do a QPE for chemical estimation, you run at least a couple thousand times the same circuit. So you can parallelize that on 10 similar systems if they are affordable. That was the idea. But the question here is very interesting. Is how do you manage interconnect? So QPU interconnect, where you have to run a given circuit on multiple qubits which are interconnected with entanglement resources. Of course, this is going to have a cost. And there are two costs to consider. One is the cost of the entanglement creation. Then you have the efficiency of that. It's going to have a toll in the efficiency of the system, if it's an async or not async. But there's another cost which have to be embedded in the thinking, and it's the same everywhere. It's a software cost, because you will have to implement so-called circuit partitioning techniques, which will make it more difficult to distribute the gates over all these units of computing. So it's going to have a software cost. It may slow down the system. It may increase the number of physical qubits you need. It may have a toll also on the way you implement error correction to some extent. So the cost has to be analyzed in a holistic way, like we say in the paper we're preparing with Yasser. So this is a very interesting question.
Yes. I have seen one hand from Javier. I don't know if we have time for another additional question from him. Javier, let me check if I can switch off.
Hello?
Okay.
Hello, Yasser. Hello, Olivier. Thank you very much. It was really a very. Now I have a very, very quick question, because at the beginning of your part, Yasser, you mentioned this provocative paper stating that some quantum computers were prone to spending much more than classical computers. And you mentioned this photonic one, which seemed to be way above, something like 100 megawatts or something like that. Now, at the end of your talk, you announced that you were starting to analyze the photonic thing, but you're still in progress. Now, as an overall picture, is this consistent to think that photonic quantum computing is way more expensive than in terms of energy than the others, or no?
No, I would say it depends. It depends on the progress we're going to have. Even Psychoton is going to make progress. I know the roadmap. I know the efforts they're doing. They're doing an amazing work in improving their silicon circuits, both at the photonic source, then the photonic, let's say, computing, and then in the end, PNRD, so photon number resolution detectors. They do a lot of progress, even routing the signals between multiple units of processing. But on the other hand, we have companies like Candela. We also do work from the guys in Denmark, Sparrow Quantum. They want to improve the way you create deterministic sources of photons. It may reduce the cost of creating the cluster states if you use an FTQC or an ABQC model, or if you use it for kind of more classical gate-based system, like what Candela is trying to do with the Spock architecture that they published 2 years ago. So I'm hopeful that either Psychoton and the other vendors will improve the energy and the power cost of their systems. But right now, we have a big discrepancy in the plans. That's what I would say. So, and there's another one, which is maybe controversial, is I don't like when those guys says we work at room temperature. It's not true. They don't run at 10 millikelvin like superconducting qubits, but they need 4K all over the place. Psychoton is using a helium factory that's the size of CERN and ITER to cool the system. So there's cryogenics involved.
Yes. Thank you very much. That was very, very
Yeah, just to clarify, Javier, so these slides that you mentioned at the beginning, they were actually from Olivier, not from me. And on our side, yes, we want to understand exactly the details of this photonic quantum computation at these different levels that I mentioned before. And indeed, I think Olivier explained very well. Many of these things are not room temperature. They will require cryogenics, and the cryogenics can be pretty dominant. And in the case that was discussed, I think it's maybe even the biggest one.
Thank you. Excellent.
Maybe get the last question on sensing and other tech. On sensing, I would say that, to be blunt, nobody cares. Let me explain why. There's no volume yet. I mean, it's probably small, mid-sized devices, not big size like FTQC systems. We don't know yet if there's going to be a volume market there. But at least in some situations, I think companies will care about that because they want to miniaturize the systems. They all dream about to get a PMT system in a car. So if they want to do that, they need to have something that costs less than $100, and that's very low power because you can't have much power be consumed in a car. But now there's another thing, which is communication. And there's a link with Spain because one of the first team working on that is from ICFO in Barcelona. By the way, they're going to make a talk at the workshop in Barcelona. So the team with Raja Heya, Federico Centrone, those two guys and the team and other partnerships in Europe, they are really looking at the energetic cost of communication. It's probably less mature than what has been done in the last 4 years in computing, but it's an emerging field. And we may guess that at some point there's going to be some scale deployment of at least QKD systems and then quantum communication for interconnecting computers. So it's worthwhile to work on that, and Spain is leading that.
And I wanted to add, just complement the great answer by Olivier regarding sensing. I mean, all these things with miniaturization, ultimately, this will probably become quantum chips. So to understand the efficiency, the energetic efficiency of these quantum chips will be relevant for miniaturization, for things that you want to go to space, where the energy budget is really, really important. Also, unsurprisingly, the cooling systems, etc., have a dominant effect. So these are all things that need to be considered. So I think all this research can also feed and benefit, and maybe even vice versa, these other quantum technologies. Ultimately, these will all be quantum chips.
Okay. I'm sorry, but the discussion is really amazing and interesting. But the problem is that we have to close because we are out of time. In fact, almost 10 minutes later than expected. Thank you very much for your knowledge, for your transfer of knowledge in this fast presentation. Clearly, we have to wait for your preprints and study them very deeply. And of course, we have to attend the next workshop in May in NIFCO about the Quantum Energy Initiative to know more about this part. People like me that work for a supercomputing center know that energy is a limiting factor in all the computation. You, Olivier, presented very well. The problem is sometimes we don't have enough energy to deploy the new systems because it's very costly. So, but we hope, or at least in our supercomputing center, we hope that the energetic cost of the quantum computer will be less in the future. We have to implement many improvements in the technology in the future, but we hope that at least if we cannot improve the energetic cost, at least we can calculate something different or using different techniques to solve current unsolved problems that we have in the classical computing area. Thank you very much for both of you. Thank you very much for the people that attend this webinar that will be available in the TalentQ platform in the next weeks. Let us some days to prepare the presentations, the video. And I hope that you can join to the next webinars that usually are every 15 days. And so look at our website periodically in order to see what is the next one that I have to know that currently I don't know which the next one. Thank you very much and welcome everybody to TalentQ. Okay.
Thank you very much.
Thank you very much.
For the participation.
Thanks for hosting us. Yes. Bye-bye.
Bye. See you. Bye. Thank you.